It's very sad. Thanks. Well, 45 minutes of... Yeah, thanks for that. Oh, wait, sometimes I forget. Great. So now we're just going to practice this. I just said a bunch of words. Let's see if it makes sense. All right, what's the direction of angular velocity? If viewed from above, an object is going clockwise. You need to draw this and then do the whole hand thing. Drawing it makes it so much easier. Either you can burn more either you can make your brain burn more calories or use way less calories. Just draw a picture real quick. Work smarter, not harder. And writing down things is working smarter. Yeah. Yep. I'm always going to give you a proper answer. It's the easiest one. Yep. Yeah, pretty much always I give it from my video. Because honestly, the test where it is, drawing a picture of it all. So, yeah. I don't All right, what did you all say? Draw it on your paper. It's going to be the easiest way. Good. All right, now go ahead and make your fingers do the thing. So you need your fingers to line up with that arrow. Yeah. So you need your, which way is your thumb pointing? Relative to this paper, down would be this way. Yeah. And to clarify here, down is this way. So up is this way, down is this way, into the board. So I'm going to teach you all some new kind of notation. Into the board is this X. It literally means going into the page, into the board, into whatever your thing you drew it on. The reason I drew this X and this dot, if you all think of like a bow and arrow, you know you shoot up, like literally like an arrow you shoot from a bow. If you all think of an arrow, what do you see at the back of the arrow? The feathers. So if you all saw an arrow getting shot into the board, you'd see the back of the arrow. What would you see at the back of the arrow? You'd see the little feathers at the back. If you saw an arrow getting shot out of the board, what would you see? You'd see the tip of the arrow. You'd see a little dot. This is the notation we use in physics for into the board and out of the board. X for into, dot for out of, and think of literally like an arrow you shoot. That's how I remember it. If you saw an arrow going into it, you'd see the feathers at the back. If you saw an arrow coming out, you'd see literally like the dot coming at you. It makes it really easy to remember. All right, so make sure whatever answer lines up with one of those vectors. That's the same one.
Because we were saying this was used before. But this in this scenario, this is not.
No, yeah, so you need to orient your picture. So this is why you want to draw it on your paper. That is the, I mean, if you took this and you wanted to make it match mine, you would need to hold it so it matches. Yeah. Because when I draw it up there, my picture is like this. So you need your, so that's why I just draw it on your paper.
I'm just clarifying that I wrote this note the right way. So if you're speeding up and your acceleration is speeding up, it's in the same direction as your velocity.
Yeah.
And then if you're slowing down, it's down.
Are they helping each other or hurting each other? That's, yeah, that's the idea. And it's going to be the same thing here. All right. So I'll close this out in 5, 4, 3, 2, 1. Oh, so many people. If you haven't drawn it, it's really hard to do this without drawing it. It's really hard to explain this without drawing it. All right, and close. All right, you need to draw this on your picture so you can make your hand match the picture. If you don't draw this, it's really hard to like show you all what's going on here. So imagine this is my paper. This could be your paper. I don't care. It doesn't like paper, board, whatever. Great. You take your hand. You make your fingers curl this direction. Just make your fingers match that. Like, boom. Which way does my thumb point? Into the board. Done. You gotta draw it, and then you literally just make your hands match the picture. Into the board, into the paper, into the surface, whatever you draw it on. That's why you need to draw it. Make your fingers match and point into it. Oh, and reminder, it's called the right hand rule. If you use the wrong hand, if you use your left hand, you get the wrong answer. If you use your left hand, you get out of the board, which is wrong. My fingers are curling the same way and I get the wrong answer. Right hand rule. My best guess is they decided this because the predominant people were right-handed. Sorry, left-handed people. You live in a right-handed world. It's a rough life. Yeah. Yeah. I can almost guarantee you any problem I ever going to give you is going to be viewed from above like this. I'm never going to give you a problem that's like this. Like it's so hard to give you a different example. So whatever. Into the board. Yeah, that's why I drew the arrows on there. Up would be.
Oh, I was okay.
All right. Great. Let's make this one different. Actually, do I want to change this? Shape outline through the power of wow. All right. Okay. A piece of gum is stuck to a tire that's spinning faster and faster. It's spinning counterclockwise as shown. If the piece of gum is on the right side, what's the direction of angular velocity? Counterclockwise. I just changed the problem, so if you download the PowerPoints, it said clockwise. Use the one that I just punted to your phones or devices or whatever. Counterclockwise. Make sure you do this one. It should have gotten punted to your phone. Make sure your hand matches whatever just got sent to your devices. Good. Now, the only way that would be up and down is if I could somehow word a problem where it was like going in a circle like this. But my gosh, I have no idea how to word a problem that's like clear to everyone. So pretty much I always have to give it this way just so you actually understand what I'm even asking for. Yeah. Yeah, you could, and then you could say it's spinning on the XY plane. But oh my gosh. I haven't trained you all in thinking about the XYZ. Like, if I say it's on the plane, no one's going to know what that means.
Would it be correct to say, like, let's instead of
Directing directly at it from what side? Yeah, that's why I have to say viewing it from a...
Okay. Yeah.
You can imagine a car going in a circle if I viewed it from...
Right.
Yeah.
Okay.
Yeah, it's not... In general, I just kind of give the picture, to be honest. All right, 10 more seconds. All right, 5, 4, 3, 2, 1. Ka-chow. All right, you do the hand thing. You make your fingers curl. You make sure you're using the right hand, literally like the right, not left hand. And you curl it, and your thumb points out of the page. So you make your fingers curl this direction. Look, there they are. There's fingers, right? I don't know. Look, there's different sized fingers, and my thumb points out of the page. It's awful. Hate it. It's really hard to draw these things, but you get the idea. Curl your fingers, points out of the page. It's the exact opposite as the last problem. Great. All right. Now let's see if you're able to connect what you learned. Let's see if you understand acceleration. All right. A piece of gum is stuck to a tire that's spinning slower and slower. If the wheel is spinning clockwise and the piece of gum's on the right side, what's the direction of the angular acceleration? Last problem, angular velocity. This problem, angular acceleration. Be careful. Think through acceleration. Should the acceleration be the same direction as velocity or the opposite direction of velocity? That's the way to think about acceleration. Same direction as velocity or opposite direction of velocity?
The velocity is going into the page, so then the acceleration will happen.
So which way is angular velocity? Angular velocity is into the page. And it's doing the opposite. Yeah. It's the opposite direction. Yeah. You always find angular velocity, and then you say my LPA. Find the direction of velocity. Find it more that way or opposite. All right. Let's say all over here. Let's say all here. All right. Let's see. Okay. Nice. All right. I am very, very happy to see people have the idea of acceleration. Very happy. So, what's the direction of angular velocity? And should I be in the same direction or opposite direction? That's the thought process. So, give you all like 5-10 more seconds to put your final thoughts together. I can almost guarantee I'll put a problem like this on the test. They're easy to make. I'll underline like slower and what you're solving for just to make sure you don't make a silly mistake. All right, 5, 4, 3, 2, 1. Is it good? All right, great. All right, so remember, we don't jump straight to angular acceleration. We got to figure out which way we're moving first. If we don't know which way we're moving, quote unquote, we can't figure out what the direction of acceleration is. So great. Which way is the angular velocity? You curl your fingers, and angular velocity is going to be into the page. So that, remember, this little X is into page. Looks a little silly, but it's the notation we use. X, remember the arrow. Am I making that increase or decrease? Decrease. So which way is angular acceleration going to be? So angular acceleration has to slower. Angular acceleration, let's quote unquote, fights this, so opposite direction. It sounds a little silly, but if it helps you remember. So the answer is into the nope. Out of the page. Yeah, I hate that, right? And I ideally would like fit it on here, but I think I don't really have room. So angular is into page, out of page. It all gets mixed up, right? Out of page, great. It's opposite. All right, this one I'm just going to give you the answer. We're not going to do it as a class. It's whatever. It's good practice. Here we go. This one's spinning clockwise. It's slowing down. I think we literally just did this one. I think these are the same thing. Yeah, but this one I was kind of underlined it. Whatever, it's the same problem. So delete that one. Okay. I don't know if we're going to be able to solve any angular kinematics. Maybe we'll do like one problem. All right. I've already mentioned this. All the kinematics equations you know, we're going to use the exact same equations. We're just going to make the swaps. So great. There they all are. This might be like, whoa, oh my gosh. I really hope the left side of this is not new to you. I really hope this left side, you're like, oh yeah, I recognize these. The right side is the exact same thing. We just swap everywhere x is, put theta. Everywhere v is, put w. Everywhere a is, put alpha. It's the exact same equations. It's the exact same process. The only thing you got to be careful of is you are either work in translational or work in rotational. Do not mix and match. I don't want to see you have any equations where you have theta in it and you also have velocity. Like, pick one side and work with that one side. Working in translational, do not mix and match variables. You should never have an equation where you decide to put omega instead of v. That'd be bad. So, anywho. All right. Great. Let's try. Let's see. Do I want to do this one? Revolutions per minute. That one might be a little. Is this one worse? All right. I think we are going to do this one. It's really not that bad. You're looking at me like, oh my gosh, this thing, wow. It's really not that bad. It looks worse than it is. We got like 20 minutes. This is a good one for us to do. It's just kinematics. It's like, oh my gosh, one part at a time, y'all. Look, I'm going to make the problem look so much easier. Just like, don't look at the next parts until you get to them. Wow, I made a paragraph into 2 sentences. That's way less intimidating. And then, then we add another part. Remember, a complex problem is just a bunch of simple steps strung together. Like, that's true of anything you ever do in life. Walking is really complicated if you think of all the motions, but if you break it into pieces of what every part of your body does, it's a bunch of simple things. So, it's one of those skills in life. Don't be intimidated by big paragraphs. Break it into pieces. All right, try it out. I believe in you. Oh, and I'll give you all a hint for part B. What's the angle traveled in one full revolution? In radians. 2 pi. Part B, all you all need to know, like to be able to do that step is 1 revolution is 2 pi. His theta is 2 pi. Look, I even put that. How kind of me. Part B, 1 revolution equals 2 pi radians. That's the only thing you all really need to know. And you can go from there. Same techniques. We just now specify we have angular velocities, and now we also have time. We just put adjectives in front of it.
Did you square it? Meters squared? No.
Nice. Part A is super easy. Yeah, it's literally that easy. It's literally that easy. Yep.
That's why I was confused.
And we put negative because we'll say it's, yeah. I mean, yeah. I chucked it there. So it's going to cause the wheel to slow. If we call angular velocities positive, we'll call this negative. So part A is super easy. It's so easy. Like, trust me. You'll believe me once you see it. Part B, you just need this fact I gave you, and then you got to think of, okay, what can I solve for to figure this out? And I'll put that on the solution. What's given? Go through what's given. What are we solving for? What's given? Is there any relationship? Yeah, so what's the second radius? R equals that. Alright, what else is given? So the unit mass
If it's in meters per second squared,
so acceleration. Yeah, radius. What am I solving for?
Show me what you have so far.
It's just go through the motions.
So,
If you all are stumped, go through the motions. What's given? Write in variables. What are you solving for? Write in variables. Don't just go through the motions. Go through the process. It will get you there. All right, so in part A, I have acceleration is -7 meters per second squared. I have the radius is 0.28 meters. What am I solving for? Someone tell me. I believe in y'all. Angular acceleration. What's the symbol for angular acceleration? Funny A, alpha. The OGA. Well, I don't know if it's OG. Maybe there's something before it, but it's before the English alphabet. All right. Is there a relationship between A, R, and alpha? Remember, this is the critical thinking process. What do I need? What do I have? What's the relationship between them? Is there an equation that relates these three variables? Y'all tell me. Does anyone know the expression between A, R, and alpha? A equals R times alpha. How do you all go from angular to regular? You multiply by R. How do you go from angular to regular? Multiply by R. These are in the formula sheet, but also they're very easy to memorize because it's just like every single angular version multiplied by R. Kind of, sort of. Kind of, sort of. So this is where I told you all it's super easy. If you didn't believe me, now hopefully you see how easy this one is. And don't forget your units. Angular acceleration, instead of meters per second squared, it's angle per second squared. What's my unit for angle? Radians. There you go. Easy, right? So this first one is just showing you, hey, we got relationships between angular and linear. Great, awesome. Part B, how many revolutions do the tires make before coming to rest? Given that their angular velocity is 95. Hey, we got a new given. Let's chuck that in there. New given, we can chuck that in. What's the symbol for angular velocity? The weird W. It's called lowercase omega. Remember, go through the same steps. Make sure when you're writing your givens, use the variables. It's going to help us find the right equations and all that good stuff. Great. I got my initial angular velocity. I have my angular acceleration. Now, we are solving for the revolutions. And this is where I gave you all a hint because we haven't seen this yet. But now that we've seen it, how do we solve for revolutions? If we know that one revolution is 2 pi radians, what is 2 pi radians a measure of? Is it a measure of velocity, acceleration, distance, angle, angular velocity? It's kind of a distance, but a distance, not circumference. Keep going, keep going. 2 pi radians is a, if I told you 360 degrees, they're the same thing. 360 degrees is a measure of, and yeah, it's the angle. So yeah, this is the key here. Radians is a measure of angle. So the key here, if you ever want to find revolutions, if you can find how many angles you went through, if you can find how much my angle changed, divide it by 2 pi and that tells you the revolutions. If you all solve, let's put it this way. Wow. Yeah, how do I want to put that? If you all can find the final angle, divide that by 2 pi, and that tells you how many times I made a circle. So here's an easy example. Theta phi is 6 pi. How many revolutions is that? If I've gone an angle of 6 pi, how many times have I gone in a circle? 3. How did you get that? 6 pi divided by 2 pi. So find the angle, divide it by 2 pi, and that's how many times you went in a circle. Every circle is 2 pi. So how many times did you do that? So look through your kinematics equations. Given initial angular velocity, given angular acceleration, how can I find final? Oh, we know one more given. What does the car do at the end? What's it? Let's just chuck this down there. If it stops, there's 2 variables that tells us now. What are they? Final velocity, and there's one more. Where do I want to? Oh, I'm still running out of room. All right, I'm going to steal all this and put it on the next slide. Once you all do a couple of these problems, stuff will click. If right now you're like, oh my gosh. Final velocity is 0. Something else is 0. We know a new thing. Now, yes, final acceleration. We're going to say the acceleration is constant. If the car is not moving, are the wheels still spinning? So what does that tell us about? That tells us a variable, a new variable. The angular velocity is also 0. If the final velocity is 0, the angular velocity is 0. Remember, you're just multiplying by r to get from one to the other. If you're not moving, your wheels ain't spinning. If your wheels ain't spinning, they're not spinning. Like that's, yeah. Angular velocity is whether you're spinning and how fast. So yeah, just look through your kinematics. You have final velocity, quote unquote. Initial velocity, quote unquote. And I'm going to make this a little better. You are technically finding the change in angle. Theta final minus theta initial. How much did my angle change? How many degrees did my wheel rotate through? Try it out. Look for the equation. That's going to be hunting. At this point, I'm going to be going around and just checking, can you find the right equation, given what you have.
Oh no, I was no.
All right. We're solving for that. Do you know the final angular velocity? Do you know the initial angular velocity? Do you know alpha? It works, just like kinematics. Yeah, so here we're kind of like finding the distance. Then we're going to convert that to rough distance. Well, the hope is that this is something you're very kind of ready to learn. Energy's so good, yo. It's so, well, I'm sorry, we're going to do energy again. But it'll be a good reason. I think the second time you see it, you're going to be because you already see it. Literally, all we're going to do with energy is say we have new energy. We're just going to say, are you moving? So, if so, you have kinetic. Are you above or below zero? So, you have potential. Is there a spring switch or stretch? That one's just a spring switch. And now we're just going to say, is it spinning? And we'll have a new energy term for that. That's it. They're like, and then it's the exact same. It's the exact same. Like, what do I start with? What do I end with? Is there work done? Alright. Y'all find the equation. Give it what I have. Alright, let's go on. Nice, there they are. What are we solving for?
So I think some.
Do you have final angular velocity then? So we have initial angular velocity. Do we have the angular acceleration? No, we got it here. Tuck it in there. I'm going to tell you how much it is. Go from revolution.
Yeah, I got it.
I want to go from angle to how many angles are at one? So that would be degrees and radians. Everything we're doing is so, say you find this angle is 8 pi. How many revolutions?
Oh my god, you're freaking just nowhere near.
So, now this is something not from the pi. Number. I'm actually creating the same law. Divided by 2 pi. That's literally how many times. All right, so if you haven't found the equation yet, again, think of it like kinematics. It's just all chuck the word angular in front of everything. I have angular velocity final, I have angular velocity initial, I have angular acceleration. I want to find the change in angle. It's this one. Omega final squared equals omega initial squared plus 2 alpha. Change in angle. Solve for change in angle. So 0 squared equals 95 squared. You see why it's important that we put this negative here? Because if I don't put the negative, I'm going to say it's speeding up. And if I speed up, I don't get to 0. Your math literally will not work. You'll get something crazy. So this is why we had to put that negative. I'm not helping, I'm hurting. I'm slowing it down. It needs to be opposite sign. So 95 squared divided by 50 equals, I don't know what. So theta final minus theta initial. I can't do that in my head. $95 squared divided by 50. This is not how many revolutions. This is not how many revolutions. This is how much my angle changed. How do I go from angle to how many angles in a revolution? How many radians in a revolution? If you all want to go from radians to revolutions, do your unit conversion. How do I do this? How many radians are in a revolution? For one revolution, there's 2 pi. You divide by 2 pi. One full circle is 2 pi. How many times did I do 2 pi is the question. So I just divide to figure out how many times that happened. And just be careful in your calculator when you're dividing by 2 pi that you put the parentheses on the bottom. I made 28.73 revolutions. I did 2 pi 28.73 times. I made a circle. Then again, then again, then again, then again, then again, you know. All right. Yeah. How did I get the 108.5? I solved this equation. So we have the initial angular velocity, we have the final angular velocity, we have the angular acceleration. Okay, yeah. So I just solved for it. It's just like a kinematics problem. All right. I'm not going to do part C because I want to give us a break and then do the lab. Part C, what are we solving for? Time. You just do, it's a kinematics problem. You all have everything. You all have the angular, quote unquote, distance. You all have the angular velocity. You all have the angular acceleration. Just choose the kinematics problem. Just choose the kinematics equation that solves for time. You got like 3 choices. This is fine. It's just kinematics. It's just kinematics. It's fine. As long as you are cool with the kinematics equations and you're cool that to go from angular to linear, you multiply by r. All right, take a breather. We'll resume at like 9:28. Yeah.
So I have the 180.5.
So you got to be careful that your 2 pi is in parentheses, because what you did here is you divided by 2 and then you multiplied by 5.
Okay, so I should do something.
It doesn't, yeah, when you put them right next to each other, it doesn't know to divide by both of them.
It's right here.
Yeah.
Okay.
Yeah, because literally what it was doing, yeah, it doesn't know to divide by both unless you tell it to multiply by both. Yeah. Yeah, let me delete that. We're doing the center of mass lab.